Imagine an AI with 1 trillion parameters. That is 1,000 billion adjustable numbers, an absurdly large digital brain. At first, you might assume every single one of those parameters must wake up, calculate, and consume electricity every time you ask it a question. If that were true, trillion parameter AI would be painfully slow, unbelievably expensive, and limited to only the biggest data centers on Earth. But here's the surprise. Some trillion parameter models can answer a prompt using roughly the same amount of computation as a model with only 30 billion parameters. Not because the trillion parameter model is pretending to be smaller, but because at any one moment, it is only using a tiny fraction of itself. This matters because it changes the economics of intelligence. The question is no longer how big can we make an AI? The question becomes, how big can we make it without paying for the whole thing every time? And the answer comes from a deceptively simple idea. Instead of asking one giant brain to think about everything, build a crowd of specialists and ask only the right specialists to work.
Let's start with the ordinary kind of neural network. Picture a giant layer of neurons as a wall filled with tiny calculators. When a word enters the model, say the word Saturn, that information flows through the network. In a traditional dense model, nearly every calculator in the relevant layers participates. Every input activates a huge amount of computation. That's called a dense model. Dense because the work is spread across almost all of its parameters. If a dense model has 30 billion parameters, then during each token prediction, it may use computation connected to most of those 30 billion parameters. Ask it to generate one word, then another, then another. And each step involves a massive coordinated calculation. Now scale that exact design from 30 billion parameters to 1 trillion. You have just multiplied the available knowledge and capacity enormously. But you have also multiplied the cost of every single thought. That is the central problem. More parameters can make a model more capable, but if every parameter must participate in every token, inference becomes brutally expensive. So researchers found a workaround.
The workaround is called a mixture of experts, often shortened to MOE. Think of the model not as one monolithic brain, but as a company with hundreds of expert teams. One team may become unusually good at code. Another may specialize in grammar. Another may handle mathematical reasoning. Another may recognize patterns in many languages. The trillion parameters are distributed across all these experts. But when the model reads a token, it does not send that token to every expert. Instead, a small routing network, sometimes called a gate or router, asks, which experts are most useful for this specific piece of information? Then it selects only a few, maybe 2 experts, maybe 8, not hundreds. So if the full model contains 1 trillion parameters, perhaps only around 30 billion parameters are actually active for a particular token. The model is still huge. Its total capacity is still 1 trillion parameters, but its active computation is much smaller. It is like having a library with 1 million books, but when you ask about black holes, you consult only the This sounds almost too good to be true. More total knowledge, less computation per answer. So what's the catch? First, the model still has to store all 1 trillion parameters somewhere. Even if only 30 billion are active at a time, the full model must exist across many accelerator chips. That requires enormous memory. Second, the selected experts may live on different machines, so the model has to move data across a network, sending each token to the correct expert and collecting the results. That communication can become a bottleneck. Third, routing has to be smart. If the router keeps sending difficult problems to the wrong experts, performance suffers. And if too many tokens all choose the same expert, That expert becomes overloaded while others sit idle. So MOE models are not free. They trade one kind of cost, raw arithmetic, for other challenges: memory, networking, balancing, and engineering. Still, the trade can be extraordinarily valuable, because in AI, the expensive part is often not owning a giant model. It is paying to use that giant model billions of times. Sparse activation makes that bill much smaller. So when someone says a model has 1 trillion parameters, remember, that number describes the model's total capacity. It does not automatically tell you how much computation happens for each word it generates. A dense model says, every part of me contributes to every thought. A mixture of experts model says, I have many capabilities, but I will activate only the ones I need right now. That is why a trillion parameter AI can run like a 30 billion parameter AI. Not because the other 970 billion parameters disappeared. They are waiting in reserve, like specialists standing behind a door, ready to be called when the problem matches their expertise. This idea is called sparse computation, and it may be one of the most important ideas in modern AI. Because the future of intelligence may not come from making every model component work harder. It may come from making models better at deciding which parts of themselves should think at all.